We spend pretty much our entire lives clicking, typing, and swiping, but have you ever stopped to think what's actually going on inside that machine of yours? Today, we're going to peel back the layers. We're diving into the elegant, lightning fast dance of logic and electricity that makes it all possible. So let's pull back the curtain and see how your computer really, truly works.
I mean, it feels instant, doesn't it? You click an icon, a program opens, boom. But in that tiny fraction of a second, an incredible sequence of operations kicks off inside your computer. It's not magic, not at all. It's a beautifully designed process. And right now, we're going to trace every single step of that journey.
To understand any complex machine, you really have to start with the blueprint. And for a computer, that blueprint is split into two really important concepts. Its architecture and its organization. You can think of it as the difference between what a building is for and how it's actually built, with all the pipes and wires and concrete. So what's the actual difference here? Well, architecture is the what. It's everything a programmer can see, the basic rules of the game. Stuff like the instruction set, what commands the computer understands, or how many bits it uses for data. Organization, on the other hand, is the how. It's all the behind-the-scenes stuff, the hardware that the programmer never sees that makes the architecture a reality. We're talking control signals, specific memory chips, all the nitty-gritty engineering details. This example just cuts right to the heart of it. The architect, the person designing the system, decides, okay, our computer needs to be able to multiply numbers. That's an architectural decision. Then the engineer comes in and says, all right, how are we going to do that? Do we build a special, super fast piece of hardware just for multiplying? Or do we save some money and just tell the computer to do addition over and over again really fast? That's an organizational choice. See? The programmer gets the same result either way, but how it happens is totally different.
Okay, so with the master plan understood, let's meet the workers. A computer is, at its core, a factory for processing information. And this factory has three main departments that you absolutely have to know about.
First up, you've got the factory manager. This is the central processing unit, or the CPU. It is the absolute core of the machine. It controls every single operation, it crunches all the numbers, and it basically tells everyone else what to do. It's the brain of the whole operation. Next up, every factory needs a factory floor, a big workspace, right? Well, that's main memory, which you probably know as RAM. Think of it like a huge workbench. When you open a program or a file, it gets spread out on this workbench so the CPU can get to it instantly. And finally, how does the factory talk to the outside world? That's where the shipping and receiving docks come in, the input/output systems, or I/O. This is everything from your keyboard and mouse, which put information in, to your monitor and printer, which get information out. It's the computer's senses. So now that we've had the grand tour of the factory, let's zoom in. Let's get a look inside the manager's office, the CPU itself. Because it isn't just one single thing. It's actually a whole team of specialists working together at mind-boggling speeds. Inside that CPU, you've really got three key players. First, the control unit. This is the foreman on the factory floor. It reads the instructions from memory and directs the entire workflow. Then you have the arithmetic and logic unit, the ALU. This is the specialist, the heavy-duty machine that does all the actual math and makes logical comparisons. And finally, you have registers. Think of these as tiny, ridiculously fast storage spots, like a little workbench right on the CPU chip, for holding whatever the ALU is working on at that exact moment. So we've met all the components, but how do they actually work together to run a program? This is where it all comes together. We're going to follow a single command on its journey through the system, from memory all the way to execution. Now, this whole process is only possible because of one brilliant, game-changing idea, the von Neumann architecture. See, before this, the instructions for a program and the data that program used were often stored in totally separate places. The revolutionary idea here was to store them together in the same memory space. This meant the computer could treat a program just like any other piece of data, which made it incredibly easy to load, change, and update software. It is, no joke, the foundation of pretty much every computer we use today. And that architecture enables the computer's fundamental rhythm, the instruction cycle. It's a simple four-step loop that happens billions of times every second. First, the control unit will fetch an instruction from memory. Step 2, it will decode that instruction to figure out what it's being asked to do. Third, the instruction gets passed over to the ALU to be executed. That's when the math or logic happens. And finally, the result is stored either in a super fast register or back in main memory. Fetch, decode, execute, store, over and over and over again. So that little four-step cycle, that's the engine of all computing. And for the last, 50+ years, the entire goal of computer design has been to make that engine run faster and faster and faster. You've probably heard of Moore's Law. It was an observation by Intel co-founder Gordon Moore that the number of transistors we can cram onto a chip doubles about every 18 months. And for decades, this law has been the driving force behind the incredible exponential growth in computing power we've all experienced. But this incredible speed-up created a huge problem. The CPU, the brain, got ridiculously fast, but the main memory, the workspace, well, it just couldn't keep up. This created a classic bottleneck. The processor is screaming for more data, but it has to sit there, waiting as it's slowly retrieved from memory. All that valuable processing time is just lost. So how did engineers solve this? Well, they came up with a brilliant trick called cache. Cache is a small, extremely fast, and very expensive layer of memory that sits right next to the CPU. It basically acts as a little stockpile of the data and instructions the CPU is using most often. That way, the CPU can check the cache first, and if what it needs is there, boom, it avoids that long, slow trip to main memory, keeping the engine running at full speed. Of course, cache wasn't the only trick up their sleeves. Engineers also developed things like pipelining, which turns that instruction cycle into an assembly line. While one instruction is executing, the next one is already being decoded. And then they created multi-core processors, which is basically like putting several brains on a single chip, letting them work on different tasks all at the same time. So there you have it, from architecture and organization to the journey of a single instruction to that constant battle for more speed. That is the fundamental story of how your computer works. But Moore's Law is slowing down. We're running up against the hard physical limits of how small and how fast we can make these things. So the big question is, what's next? Where will the next big breakthrough come from? Will it be new materials, quantum computing, or some completely new kind of architecture we haven't even dreamed of yet? That's the challenge for the next generation of engineers.